What if most of the matter in the universe is not only invisible, but far stranger than science first imagined? For decades, dark matter seems like a simple missing piece, a hidden mass shaping galaxies from the shadows. But the deeper astronomers look, the weirder it becomes. If this journey into the dark side of the cosmos sounds fascinating, please like the video, subscribe to the channel, and settle in for a calm exploration of one of the greatest mysteries in modern science. At the widest scale, the universe presents itself as a place of light, distance, and motion. Telescopes gather starlight from nearby stars, faint light from distant galaxies, and older light that has travelled across most of visible cosmic history. This display seems full. Galaxies spread across the sky in immense numbers. Gas glows inside them and between them. Dust dims and reddens light as it passes. Stars burn, explode, and leave matter that later forms new stars and planets. Yet when astronomy attempts a full inventory of what the universe contains, the bright and familiar part becomes a small fraction of the whole. The first impression of abundance gives way to a quieter result. Most of the cosmic content does not shine. In this broad accounting, ordinary matter means matter made of atoms. It includes stars, planets, gas, dust, people, oceans, rocks, and every visible structure that telescopes record through light. It also includes dim material that does not glow much at all, such as cold gas clouds and the faint remains of old stars. This ordinary material appears in many forms, but it shares one common property. It interacts with light in ways that can be traced. It can emit light, absorb it, scatter it, or block it. Because of that, astronomy can estimate how much of it exists, even when it is difficult to see directly. Over many decades, that estimate grows more precise. The result remains surprisingly small. Modern cosmology, the study of the universe as a whole, builds this inventory from several independent lines of evidence. It compares the glow left from the early universe, the large patterns of galaxies across space, the motions of matter under gravity, and the measured rate of cosmic expansion. When these observations are fitted together, they describe a universe in which ordinary atomic matter contributes only about 5 parts in 100 of the total cosmic energy budget. A much larger share belongs to dark energy, the name given to the cause of the present accelerated expansion of space. Another large share belongs to dark matter, which does not emit, absorb, or reflect light in any known ordinary way, but whose gravity helps shape the cosmos. These names describe what these components do in observation, not what they are in essence. Dark matter is not proposed because astronomers fail to look carefully enough, or because some ordinary material remains hidden in shadow. The inventory already includes faint stars, cold gas, hot gas, dust, and compact remnants wherever they can reasonably exist. It also accounts for the matter expected from the early nuclear history of the cosmos, when the first light elements formed soon after the hot beginning. That early history leaves narrow limits on how much ordinary atomic matter the universe can contain. Later observations of the relic glow from the young universe support the same conclusion. The total amount of ordinary matter is not large enough to explain the full gravitational behavior seen on cosmic scales. Something else appears to add mass without adding light. At this outermost level, dark matter enters not first as a particle or a substance in a laboratory, but as a bookkeeping necessity in the cosmic census. The universe behaves as though much more matter exists than telescopes can directly inventory in atomic form. This statement remains cautious. It does not yet say what the unseen matter is made of. It does not yet say whether it comes as one particle, many particles, or some more unfamiliar arrangement. It only says that when the contents of the universe are weighed through their effects, the visible share falls far short. Gravity seems to be responding to a much deeper reservoir. Even this broad statement requires care, because the cosmic budget mixes mass and energy in one framework. In modern cosmology, matter and energy both influence the geometry and expansion of the universe. For that reason, astronomers often describe the cosmic inventory as a budget of total energy content. In that budget, dark matter contributes far more than ordinary matter, but far less than dark energy. Ordinary matter supplies about 5 parts in 100. Dark matter supplies roughly 1/4. Dark energy supplies roughly 2/3. The exact values depend on the data set and the model details, but the broad picture remains stable. The luminous world, with all its stars and galaxies, is a minority presence in the grand account. The case for taking this inventory seriously becomes stronger because the same broad fractions appear from different directions. Observations of the early relic light indicate one set of proportions. Surveys of galaxies across immense volumes support compatible values. Measurements of how structure grows through cosmic time also point in the same general direction. No single measurement is perfect, and some tensions remain in modern cosmology. Yet the repeated convergence matters. It suggests that dark matter is not a narrow fix for one isolated problem, but part of the larger framework that allows many observations to stand together without contradiction. In that sense, dark matter first appears not in a hidden object, but in the deep arithmetic of the universe itself. At this widest level, one further distinction becomes important. Dark matter is not the same as dark energy. The two names are similar because both refer to things not directly seen, but their roles differ. Dark matter behaves like matter in the sense that its gravity helps gather structure. Dark energy instead affects the expansion of space in a way that makes that expansion accelerate rather than slow. One helps build cosmic structure. The other changes the background history through which that structure grows. Both remain mysterious, but they are not interchangeable ideas. So the outermost region of this subject is not a hidden object drifting in darkness. It is the universe viewed as a whole, where all visible things are placed into a complete account and found to be incomplete. The stars, dust, gas, and galaxies remain real and abundant. But in the widest census now available, they sit inside a much larger arrangement in which most matter is dark and most total energy belongs to something else entirely. That result does not reveal the inner nature of dark matter. It establishes the setting in which the problem appears. The first recognition is calm and simple. The universe, taken as a whole, contains far more than it shows. Beyond the broad inventory of cosmic contents, the universe shows another great outer pattern. Matter is not spread evenly through space like a fine mist. It gathers into an enormous network of strands, sheets, knots, and open regions. Astronomers call this the cosmic web. The term means the largest known arrangement of matter across the observable universe, where countless galaxies trace long filaments, broad walls, and dense intersections, while vast emptier regions open between them. The visible galaxies mark this pattern with light. But the deeper framework is not made by light alone. Observations indicate that dark matter supplies most of the underlying mass that helps this web take shape. From a distance, this structure can be pictured as a network stretched across immense volumes of space. Long filaments connect denser nodes. Wide voids lie between them. The voids are not perfectly empty. but they contain far less matter than the crowded strands. The nodes and filaments form the basic large-scale geography of the universe. Galaxies do not appear at random positions. They tend to gather where the web is denser, and they are rarer where the web thins away. This pattern is not decorative. It is the record of gravity working over cosmic time on tiny early differences in density, slowly amplifying them into the larger structures known. The first clues to this network come from galaxy surveys. When astronomers measure the positions of many galaxies over large regions of sky, they do not find a smooth field. They find chains, clusters, bridges, and walls with dark gaps between them. As surveys expand, the pattern becomes clearer. The universe begins to resemble a foam-like structure in which galaxies sit along the surfaces and threads around enormous low-density spaces. These maps are made from ordinary matter because stars and gas produce light. But visible matter alone does not explain why the pattern grows as it does. The shaping force appears to come mostly from mass that remains unseen. Dark matter matters here because gravity begins working on it early and persistently. In the standard picture, dark matter does not feel light in the ordinary way. It does not get pushed or heated by radiation as ordinary gas does. Because of that, it can begin gathering under gravity into broad, overdense regions while ordinary matter is still more tightly coupled to radiation in the early hot universe. After the young cosmos cools enough for ordinary matter to move more freely, that ordinary matter falls into the gravitational wells already deepened by dark matter. In this way, dark matter acts less like a bright substance within the web and more like the hidden mass that helps define where the web grows strongest. This does not mean the web is made of dark matter alone. Ordinary matter also joins it, especially after stars and galaxies begin to form. Gas flows along the same broad gravitational landscape. Galaxies arise in the denser zones. Hot gas fills parts of the larger structures. Yet the visible component follows a framework that appears heavier and broader than the luminous material by itself. The web is therefore both visible and invisible at once. Light shows the glowing and star-filled parts. Gravity reveals the fuller structure beneath, in this outer region of the subject. The word structure means more than shape. It also means growth through time. The cosmic web does not appear all at once. It emerges gradually as slightly denser regions pull in more matter, becoming denser still, while thinner regions lose relative influence. Over immense spans of time, this turns small unevenness into large contrast. Filaments grow more distinct. Nodes become richer. Voids expand in relative emptiness. The universe remains dynamic, but the overall pattern becomes increasingly organized on large scales. Dark matter is central in this process because its gravity helps set the pace and scale of that growth. Computer simulations show this clearly. When cosmologists begin with the slight density variations inferred from the early relic light of the universe and allow gravity to evolve them forward, a web-like structure appears. Filaments stretch across space. Dense knots form at intersections. Lower density regions widen between them. When dark matter is included in the standard way, the resulting large-scale pattern resembles the observed distribution of galaxies remarkably well. This does not prove the inner nature of dark matter, but it shows that a universe with dark matter can reproduce the broad architecture seen by surveys. The web is one of the strongest successes of that framework. The same broad picture also helps explain why the larger structures are not isolated islands. A galaxy is not simply surrounded by empty space. It belongs to a larger environment shaped by neighboring matter, past flows, and the web around it. Even the richest regions are connected to other rich regions by filaments that channel matter across cosmic distances. The web therefore gives the universe continuity. It links separated places into one gravitational pattern. That continuity is important because it shows dark matter not as a local patch or correction, but as part of a connected cosmic arrangement. Astronomers also try to map this hidden framework more directly. One method uses gravitational lensing, the bending of light by mass. If enough mass lies between a distant source and an observer, the light from the background source is slightly distorted. By measuring the weak systematic stretching of many background galaxies, astronomers can infer how mass is distributed along the line of sight, including mass that does not emit light. These measurements do not show dark matter as a bright object. They show its influence as a pattern of warped light, allowing parts of the web's invisible scaffolding to be traced. The result strengthens the idea that visible matter sits within a wider, darker structure. At this level, the strangeness of dark matter begins to deepen. It is already strange that most matter does not shine. It becomes stranger that this unseen component appears to govern the broad arrangement of the luminous universe. The stars and galaxies that seem to define the heavens are, in this picture, inhabitants of a much larger hidden framework. The visible cosmos is not the primary builder of the largest pattern. It is the illuminated surface of a deeper gravitational design. Still, caution remains necessary. Observations indicate that dark matter explains the large-scale web very well, but this does not yet reveal what dark matter is made of. It tells what role it plays in structure formation. It does not identify its substance. Some alternative ideas attempt to reproduce parts of this behavior by changing the laws of gravity rather than adding unseen matter. These ideas are studied seriously, especially where tensions or unexplained details remain. But at the scale of the cosmic web, the dark matter framework remains the leading explanation because it connects the observed growth and arrangement of structure with other major cosmological observations in a coherent way. So the second outer layer of this subject is the vast web itself. It extends across intergalactic space in filaments, nodes, sheets, and voids. It holds galaxies within a pattern much larger than any one galaxy can show. It grows under gravity from small early differences into the great architecture of the present universe. And through that growth, it presents one of the clearest signs that the cosmos is structured by a dominant form of matter that remains unseen. Within the vast web of cosmic structure, some regions gather matter on a still grand but more concentrated scale. These are galaxy clusters, the largest gravitationally bound systems in the universe. A cluster is not a single object in the ordinary sense. It is a deep region of shared gravity containing many galaxies, large amounts of hot gas, and a much greater reservoir of unseen mass. At this level, the evidence for dark matter becomes more immediate. Because a cluster can be weighed in more than one way, its visible contents provide one estimate, its gravitational effects provide another. The two do not match. A galaxy cluster appears first as a gathering of galaxies across a relatively compact region of space. Some clusters contain hundreds of galaxies, others contain thousands. Between these galaxies lies hot gas spread through the cluster as a thin but massive medium. This gas is so hot that it shines mainly in X-rays rather than visible light. In fact, in many clusters the hot gas contains more ordinary matter than all the stars in the member galaxies combined. So when astronomy examines a cluster carefully, it does not weigh only the starlight. It also counts the mass of this glowing gas. The cluster then seems full of matter in visible and measurable forms. Yet even after that fuller accounting, the total still falls far below what gravity requires. One of the oldest ways to estimate cluster mass uses motion. If many galaxies share one gravitational system, then their speeds reflect how deep that gravitational well is. Fast motion usually means strong gravity, and therefore large mass. When astronomers measure how quickly cluster galaxies move within the cluster, the result points to far more mass than the stars alone can provide. Later, when X-ray observations reveal the great cloud of hot gas inside clusters, that gas adds substantial ordinary matter to the total. But even the stars and gas together still do not account for the full gravitational pull implied by the motions. A large unseen contribution remains. This alone makes clusters important in the dark matter problem, because they are large enough to give strong signals and rich enough to allow multiple checks. But the evidence grows stronger still through light itself. Gravity bends the path of light. This effect is called gravitational lensing. The term means that mass changes the geometry through which light travels, causing distant objects seen behind a massive foreground system to appear stretched, shifted, brightened, or sometimes multiplied into arcs and repeated images. A galaxy cluster is massive enough to act as a powerful lens. Because of that, it becomes possible to map its mass not only through the motion of galaxies or the glow of hot gas, but through the distortion of background light. In some clusters, the lensing is dramatic. Background galaxies appear as long, curved arcs around the cluster core. Their shapes are not the shapes they have by themselves. They are the result of light passing through a warped gravitational region. By modelling these arcs, astronomers can estimate how much mass lies in the cluster and how that mass is distributed. In other clusters, the effect is gentler. Many background galaxies are each distorted by a very small amount. No single galaxy reveals much on its own. But when very large samples are analysed statistically, a pattern of weak lensing appears. This too maps the mass, in both strong and weak forms. Lensing allows mass to be studied whether or not that mass shines. The remarkable result is that the lensing mass of clusters exceeds the mass of the visible galaxies and hot gas by a wide margin. The cluster bends light as though it contains much more matter than ordinary observations can inventory directly. This is one of the cleanest reasons clusters matter so much in the study of dark matter. Light from the background does not care whether the foreground mass is luminous or dark. It responds to the total gravitational field. When the field is mapped, a great hidden component appears. At this scale, dark matter is not yet a subtle inner property of one galaxy or one peculiar object. It is a dominant share of the mass in an enormous system that can be observed across many wavelengths. The galaxies show where stars collect. The X-rays reveal where hot gas fills the cluster volume. The lensing pattern shows where the total mass lies. Since the total outweighs the visible contents by a large factor, dark matter becomes the simplest way to complete the mass budget. It is unseen in light, but it is present in gravity. Clusters also matter because they hold together over long cosmic times. A galaxy cluster is not a passing alignment of unrelated objects. Its galaxies orbit within a common gravitational well. The gas remains trapped in that well at very high temperatures. If the cluster did not contain enough mass, the observed motions and gas temperatures would be difficult to sustain within a stable bound structure. Dark matter, in the standard picture, deepens the well enough for the cluster to exist in the form observed. In this sense, dark matter is not only inferred from the cluster, it helps define what a cluster is physically able to be. This region of the subject also shows how dark matter becomes more convincing when different methods agree. The speeds of galaxies point to hidden mass. The temperature and distribution of the hot gas fit with a deep gravitational well. The lensing of background light independently confirms a large total mass. Each method has its own uncertainties, but they do not act in the same way. Their broad agreement strengthens the conclusion. A cluster seems to be a place where unseen mass is not an optional detail. It is part of the central architecture. At the same time, clusters reveal that ordinary matter, though not dominant, still matters greatly for understanding the whole system. The hot gas is not a small correction. It is the main ordinary component in many clusters. This means the missing mass problem at the cluster scale is not created by ignoring diffuse material between galaxies. That material is observed and included. The remaining discrepancy survives even after a serious accounting of the ordinary contents. This makes the case more robust than a simple comparison between visible stars and total gravity. Some modified gravity ideas try to explain part of the cluster evidence without invoking dark matter, and these ideas remain part of serious scientific discussion. But clusters present a demanding test. Any alternative must reproduce not only galaxy motions but also gas behavior and the detailed lensing maps. For this reason, galaxy clusters remain among the strongest large-scale pieces of evidence that most matter in the universe is dark. They do not identify the substance itself. They show, with unusual clarity, that the mass is there. So at this third level inward, the subject narrows from the grand cosmic web to the heavy knots within it. A galaxy cluster gathers galaxies, hot gas, and an even larger invisible component into one bound system. It can be weighed through motion, heat, and bent light, again and again. The result points in the same direction. The visible contents are substantial, but they are not enough. The cluster is heavier than it looks, and the hidden share is not small. It is most of the mass. When a galaxy cluster is observed in relative calm, its visible parts and its total mass can be studied together within one broad gravitational system. But there are rarer moments when clusters do not remain calm. They collide. These collisions do not resemble impacts between solid objects. A cluster is mostly space, with galaxies spread far apart and gas filling the region in a thin, hot medium. When two clusters pass through one another, the event unfolds across immense distances and over long spans of time. Yet in that slow collision, the different ingredients of a cluster do not all behave in the same way. This difference becomes one of the most striking clues in the study of dark matter. A cluster contains three main contributors to its total mass budget. There are the galaxies, each holding stars and smaller reserves of gas and dust. There is the much larger cloud of very hot ordinary gas spread between the galaxies, and there is the unseen component inferred from gravity, which in the standard picture is dark matter. These three do not respond identically during a collision. The galaxies are small and widely separated compared with the size of the whole cluster, so most of them pass by one another without direct encounters. Dark matter, if it behaves as mostly collisionless matter, should do something similar. The hot gas behaves differently. It interacts strongly with other gas through pressure and drag. When two great gas clouds meet, they slow, compress, and heat. This difference in behavior creates a natural experiment. In an ordinary laboratory, dark matter cannot yet be held, poured, or made to collide in a controlled vessel. In colliding clusters, nature provides an event on a cosmic scale in which different forms of matter are forced into different paths. The galaxies move onward with relatively little resistance. The hot gas catches and lags behind. If the main gravitational mass follows the galaxies rather than the gas, then the unseen mass behaves unlike ordinary atomic matter. It does not remain with the dominant ordinary material, it separates from it. The best-known examples of this kind of event show just that pattern. Telescopes in visible light trace the galaxies. X-ray telescopes map the hot gas, which glows because the collision shocks and heats it further. Gravitational lensing then measures where the total mass lies by following how background light is bent. When these maps are laid over one another, the hot gas often appears concentrated in a region between the two main galaxy concentrations, while the strongest lensing signal lies nearer the galaxies on either side. In simple terms, the part of the cluster made of ordinary gas is slowed and displaced, but most of the gravitating mass continues ahead. This is important because the hot gas is not a minor detail. In many clusters it contains most of the ordinary matter. If all the cluster mass were ordinary matter in one form or another, then a collision should leave the main mass much more closely tied to the gas. Instead, the lensing maps indicate that the dominant mass is offset from the gas and tracks the more freely passing components. That is the heart of the argument. The collision appears to separate where most of the ordinary matter is from where most of the gravitating mass is. The result is often described as direct evidence for dark matter, though the word direct needs care. No telescope sees a glowing cloud labelled dark matter. What is seen directly are galaxies, X-ray emitting gas, and patterns of distorted background light. The conclusion comes from the alignment and separation of those observed components. The lensing mass sits where a largely collisionless component would be expected to sit after the encounter. The gas sits where collisional ordinary matter would be expected to gather after being slowed. The geometry of the event makes the interpretation unusually powerful. The collision also helps clarify why dark matter is said to be dark rather than merely hidden. If the missing mass were mostly ordinary matter in some obscure form, then it would still be expected to share the collisional behavior of ordinary particles under these conditions. Gas clouds collide, plasma collides, dust interacts, but the dominant unseen component appears not to do so strongly. It passes through with comparatively little resistance. In the standard view, this is because dark matter interacts very weakly except through gravity. A cluster collision turns that abstract statement into a visible arrangement across the sky. This kind of evidence also places limits on how strongly dark matter can interact with itself. If dark matter particles were colliding frequently with one another during the cluster encounter, their distribution might be expected to lag more, spread more, or separate in ways different from what is observed. The fact that the lensing mass remains closely associated with the galaxies in several systems suggests that any self-interaction, if present, must be limited or subtle at the scales and speeds involved. This does not mean self-interacting dark matter is ruled out in every form. It means cluster collisions provide strong constraints on how intense those interactions can be. Alternative ideas based on modified gravity face a difficult test here. A change in gravity can alter how motions and lensing are interpreted in some systems. But in a collision, the visible ordinary matter is physically separated into distinct places. The hot gas, which contains most of the ordinary mass, ends up offset from the strongest lensing signal. Any theory that tries to explain the phenomenon without dark matter must reproduce this spatial separation while still matching the observed lensing and the behavior of the gas. That is a demanding requirement. For many researchers, This is why colliding clusters stand as one of the sharpest challenges to purely modified gravity explanations. Even so, the scientific interpretation remains careful. Each colliding system has its own geometry, viewing angle, timing, and uncertainties. The mass maps depend on data quality and modeling choices. Gas behavior can be complex. No single object carries the entire case for dark matter by itself. But taken together, these systems show a repeated physical pattern. Ordinary gas slows in collision. Galaxies pass more freely. The dominant gravitating mass tends to remain aligned with the more freely moving components, rather than with the slowed gas. That repeated pattern is difficult to ignore. At this level inward, the subject is no longer only about extra gravity in a static system, it is about behavior in motion. A cluster collision reveals that the unseen mass is not just present, it appears to act differently from ordinary matter under stress. That is where dark matter starts to seem stranger than a mere accounting term. It is not simply more mass than expected, it is mass with a different kind of cosmic conduct. So this region of the subject is defined by separation. Galaxies, hot gas, and total mass begin together as parts of giant clusters. Then the clusters collide, and those ingredients no longer stay matched in place. The hot gas is slowed and gathered. The galaxies continue. The main gravitational mass follows the path of the freer components. In that divergence, a deeper distinction appears between the luminous matter that can be heated, compressed, and delayed, and the dominant unseen mass that seems to slip through with little more than gravity to announce its presence. Around every large galaxy that fills a telescope image with spirals, bars, dust lanes, or a smooth golden glow, there lies a much broader region that does not announce itself through ordinary light. The bright part of a galaxy is only the central and more obvious portion of a larger gravitational domain. Stars gather in the visible body. Gas and dust trace arcs, disks, and clouds within it, but far beyond the last bright stars, beyond the luminous edge that seems to define the galaxy, the gravitational reach continues. This wider region is called the halo. In ordinary astronomy, the word halo can refer to several faint outer components, including sparse stars and globular clusters. In the dark matter problem, it refers more deeply to the vast dominant envelope of unseen mass that surrounds the galaxy and extends far outside the visible structure. This galactic halo is not a thin shell. It is a broad three-dimensional region, with its greatest share of matter not concentrated in the shining disk or central bulge, but spread through a much larger volume. The visible galaxy sits inside it rather than equaling it. From a distance, a spiral galaxy may look like a flat spinning system drawn in starlight. In gravitational terms, it is better understood as a bright inner feature embedded in a far larger dark reservoir. The contrast between what is seen and what is present becomes especially clear here, because the halo reaches into space where little luminous matter remains. The outer halo is difficult to imagine at first because ordinary sight gives too much authority to brightness. Human intuition tends to stop a galaxy where the light fades. Astronomy learns that the fading of starlight is not the fading of the galaxy's full mass. Beyond the visible disk of a spiral galaxy, or beyond the main glow of an elliptical galaxy, the surrounding space still belongs to the system. Sparse tracer objects can still move under its pull. Small companion galaxies can orbit within it. Faint stellar streams can arc through it. Light from more distant sources can be bent by its mass. These outer signs reveal that the galaxy is much larger in gravity than in light. The halo is also where the difference between ordinary matter and dark matter becomes more spatially obvious. In the visible galaxy, stars and gas make crowded patterns. Spiral arms hold young blue stars and clouds. Central bulges glow with older stellar populations. Dust lanes cross the disk. These structures are detailed and luminous. The halo is quieter. It is not empty, but it is far less crowded with ordinary shining matter. A few old stars may inhabit the outskirts. Globular clusters, which are dense ancient star groups, can orbit there. Thin streams of stars from disrupted smaller systems may stretch across it. Hot diffuse gas may linger through parts of the broader circumgalactic region. Yet all of this visible and measurable material remains only a small share of the halo's total mass in the standard picture. Most of the halo is dark matter. This idea changes the meaning of a galaxy. A galaxy is not simply a collection of stars. It is a gravitational system in which the stars occupy only the inner, luminous fraction of a much larger mass arrangement. The halo supplies the dominant gravitational environment in which the visible parts form and remain bound. It is the wider basin into which gas falls, the larger structure that holds satellites, and the unseen matter distribution that shapes how the galaxy lives in space. In this sense, the visible galaxy is a bright interior expression of a darker whole. Astronomers infer the presence of galactic halos through several kinds of evidence, but at this level the central point is not any one measurement. It is the consistency of a broader picture. A galaxy behaves as though its mass continues well beyond where its stars are concentrated. Companion galaxies orbit as though held by a much deeper gravitational well than the starlight implies. Distortions of background light reveal mass distributed around galaxies on scales larger than the luminous body. The statistics of galaxy formation and clustering also indicate that galaxies occupy dark matter halos of different sizes and masses. These lines of evidence together suggest that the halo is not an incidental fringe. It is the main mass container of the galaxy. The shape of a dark matter halo is still an active subject of study. In simple language, it is often described as roughly spherical, because it surrounds the galaxy in all directions rather than lying only in the flat plane of a stellar disk. But real halos need not be perfect spheres. Simulations and observations suggest they can be somewhat elongated or irregular, shaped by mergers, accretion, and the broader cosmic environment. Even so, the broad contrast remains. The visible disk of a spiral galaxy is flat and sharply structured. The dark halo is much rounder, broader, and less directly seen. One belongs to light, the other belongs mainly to gravity. This outer galactic region also preserves part of a galaxy's long history. Galaxies do not grow in isolation. Over cosmic time they gather gas, merge with smaller systems, and absorb satellite galaxies. Some of the visible traces of this history remain in the halo. A faint stellar stream may mark the remains of a smaller galaxy pulled apart by tidal forces, meaning the stretching effect of uneven gravity. A globular cluster may orbit as a survivor from early epochs. A distant dwarf galaxy may continue circling within the larger halo, held in place by mass that cannot be seen. These companions and remnants make the halo a region of memory, where the outer structure quietly records the galaxy's growth. The halo also links one galaxy to its wider surroundings. A galaxy is not cut off at its bright edge. Its halo reaches outward into intergalactic space and meets the broader matter distribution of the cosmic web. Matter can flow inward along this larger structure and contribute to the galaxy over time. Small systems can enter the halo and become satellites or be torn apart. The outer boundary is therefore not a sharp wall. It is more like a gradual transition where the galaxy's own gravitational domain becomes part of the larger environment. Dark matter is central to that continuity because the halo forms the bridge between the bright galaxy and the wider cosmic structure around it. What makes this region especially important is that it turns dark matter from a cosmic accounting term into an architectural feature of ordinary galaxies. The earlier evidence from the universe as a whole, from the cosmic web, and from galaxy clusters shows that unseen mass matters on immense scales. The galactic halo brings that hidden mass down to the scale of a single familiar galaxy. It suggests that even a graceful spiral seen through a telescope is not defined mainly by what shines. It is defined by a much larger unseen structure that holds the shining parts inside it. So this fifth region inward is the dark envelope around galaxies, the place where the visible body ends but the real gravitational domain does not. The halo surrounds, outweighs, and extends far beyond the starlit form. It holds satellites, preserves ancient traces of assembly, and joins the galaxy to the larger web of matter in the universe. In the calm language of observation, it becomes clear that a galaxy is not only a city of stars, it is a luminous interior resting within a far larger sphere of darkness. In the outer visible regions of a galaxy, the problem of dark matter takes on a form that is both simple and persistent. It appears in motion. A spiral galaxy presents a familiar arrangement to the eye. Near the center, starlight grows dense. Farther out, the disk spreads into thinner arms, with gas, dust, and scattered stars tracing broad curves around the core. As the light fades toward the edge, it is natural to expect the controlling gravity to fade with it in a similar way. If most of the mass were concentrated where most of the light is, then matter farther from the center should orbit more slowly as distance increases. This expectation comes from the same basic reasoning that describes motion around a dominant central mass. But when astronomers measure those outer motions, the result is different. The outer disk of a spiral galaxy is not empty. Even where starlight becomes faint, gas often continues outward beyond the brightest visible parts. This gas is especially useful because it can be traced through radio observations, allowing astronomers to follow motion to larger radii than starlight alone would permit. In these outer regions, clouds of gas and populations of stars still orbit the galactic center. Their speed can be measured from the shift in wavelength caused by motion along the line of sight. One side of the galaxy moves partly toward the observer, and the other moves partly away. By combining these measurements across the disk, astronomers build a rotation curve, meaning a record of orbital speed as a function of distance from the center. If the mass of the galaxy were distributed mainly like its light, the rotation curve would rise in the inner parts, where more mass is enclosed, then after a point it would begin to decline. The outer disk should move more slowly than the inner regions once most of the mass lies behind it. This is not a strange or exotic expectation. It is the ordinary prediction for systems where the bulk of the gravitating matter is concentrated toward the middle. Yet real galaxies often do not behave that way. Their rotation curves tend to remain flat far into the outer disk. Instead of falling as the light thins out, the orbital speed stays unexpectedly high. This flatness is one of the classic signs of dark matter at the galactic scale. It suggests that the enclosed mass continues to rise with distance well beyond the brightest stellar regions. In other words, matter in the outer disk moves as though the galaxy contains a great deal of additional mass spread through a larger volume than the visible stars indicate. The extra mass cannot be placed mainly in the bright central bulge or the inner luminous disk. because the outer motions respond to how much mass lies inside their orbits. To keep speeds high at large radii, the galaxy must remain massive far beyond where most of the light is concentrated. This is one of the clearest reasons astronomers infer a dark halo around galaxies. The power of this evidence lies in its regularity. It is not confined to one unusual galaxy. Spiral galaxies of many sizes show the same broad pattern, though with differences in detail. Some rise more gradually. Some show small bumps where spiral structure or gas distribution affects the measurements. But the broad message repeats. Outer matter moves too quickly for the visible material alone. The light fades, while the need for mass continues. This repetition makes the phenomenon difficult to dismiss as a local disturbance or observational accident. It appears instead as a common property of disk galaxies. The outer disk is a particularly revealing region because it lies near the edge of what appears obvious in visible light. In the inner galaxy, mass estimates are complicated by dense structures, crowded stellar populations, and the possible contribution of central components. In the outskirts, the geometry becomes cleaner. The disk thins, the light weakens, yet the motion does not drop away as expected. The discrepancy between appearance and gravity becomes more exposed. A galaxy that seems to end in starlight keeps behaving as a much heavier system. The edge of brightness is not the edge of mass. Astronomers do take care to count ordinary matter as fully as possible in these regions. They do not compare the measured motions only with the light from stars. They also include gas, especially the extended gas disk that reaches into the outskirts. This matters because gas can contribute significantly to the outer mass budget of some galaxies. Even after this gas is included, however, the rotation curves usually still require much more mass than ordinary matter can supply. The problem is not created by neglecting the diffuse outer disk. The discrepancy survives after that correction is made. Another useful feature of rotation curves is that they allow astronomers to infer not only that extra mass exists, but also something about how it is distributed. If the unseen matter were concentrated entirely in the bright interior, it would not keep the outer speeds high. The flat rotation curve instead points to a broad distribution of unseen mass, extending through and beyond the visible galaxy. This matches the idea of a dark halo surrounding the disk. The outer disk therefore serves as a transition zone, where the presence of that halo becomes dynamically hard to ignore. This region also reveals something about the relation between ordinary matter and the unseen mass. The visible galaxy still matters greatly. The inner shape of the rotation curve often reflects the distribution of stars and gas. A galaxy with a dense central concentration usually shows a steeper rise in orbital speed near the center. The luminous structure leaves an imprint. But farther out, where the visible surface thins, the continued high speed indicates that another component increasingly dominates the gravitational field. The outer disk is therefore not a place where ordinary matter becomes irrelevant. It is a place where its limits become clear. Some alternative theories attempt to explain flat rotation curves by modifying gravity rather than adding dark matter. These ideas arise partly because galactic rotation is such a basic and long-standing puzzle. In some galaxies, modified gravity can reproduce parts of the observed relation between visible matter and orbital speed remarkably well. For that reason, rotation curves remain important in debates about the nature of the missing mass problem. Yet within the standard cosmological framework, the simplest interpretation is that galaxies sit inside extended dark matter halos, and the outer disk reveals their gravitational influence directly through motion. This view also connects more naturally with evidence from larger cosmic scales. In quiet observational terms, the outer disk shows a mismatch between what glows and what governs. A spiral galaxy looks like a bright wheel turning in darkness. Careful measurement shows that the turning remains too swift for the bright wheel alone. The disk does not slow the way a light-based estimate would suggest. It continues under the pull of a more extensive mass distribution, one that cannot be seen but can be traced in every orbit. So this sixth region inward is the edge of starlight in motion. Here, the evidence for dark matter does not come first from the grand census of the universe or from immense clusters of galaxies. It comes from the quiet persistence of speed in the fading outskirts of ordinary galaxies. The light grows thin, the gas continues outward, the rotation stays high, and from that steady pattern, the unseen mass of the galactic halo becomes one of the most enduring facts of modern astronomy. The dark halo of a galaxy becomes easier to imagine in general than in detail, because most galaxies can be viewed from the outside. Their luminous shape can be seen as a whole against the sky. The Milky Way is different. It is the galaxy that contains the solar system, so it cannot be observed from a distant external vantage point. Its dark halo must be traced from inside. This makes the work slower and more careful, but it also makes it unusually rich. In the outer halo of the Milky Way, far beyond the bright disk and central bulge, astronomers use distant stars, globular clusters, and long stellar streams to map the reach, shape, and mass of the galaxy's unseen matter. The visible Milky Way is most familiar as a pale band of light crossing a dark sky. That band marks the crowded disk, where many stars, gas clouds, and dust lanes lie concentrated in the galactic plane. But the galaxy does not end there. Beyond the disk and beyond the central stellar bulge lies a much broader region in which stars are sparse. Gas is thin, and gravity still rules over a vast volume. This is the halo. Some of its visible components belong to ordinary matter. Old stars drift through it. Ancient globular clusters orbit in it. Faint streams of stars stretch across it like delicate threads. Yet these visible traces do not supply most of the mass. They serve instead as markers moving through a much larger dark structure. The outer halo is especially valuable because it reaches far from the crowded inner galaxy. Near the center and within the disk, motions are influenced by many overlapping structures. Spiral arms, gas clouds, bars, and dense stellar populations complicate the picture. In the outer halo, the environment is quieter. Objects there move through a region where the dominant influence is the large-scale gravitational field of the Milky Way itself. By measuring their positions and motions, astronomers can infer how much mass the galaxy contains at great distances from the luminous center. The outer halo is therefore like a spacious testing ground where the dark matter distribution becomes easier to study. One of the most useful traces in this region is the stellar stream. A stellar stream forms when a smaller gravitational system, such as a compact star cluster or a faint small galaxy, is pulled apart by tidal forces, meaning the stretching effect that occurs when gravity is stronger on one side of an object than the other. As the smaller system orbits the Milky Way, its stars are gradually stripped away and spread along its path. Over time, these stars form long narrow streams that arc through the halo. They do not appear by chance. Their shape and motion preserve information about the gravitational field through which they move. In that sense, a stellar stream is both a remnant and a measuring tool. These streams are important because their paths depend on the mass distribution of the Milky Way halo. If the halo were lighter, heavier, rounder, flatter, or more irregular, the streams would follow somewhat different courses. By tracing the positions of stream stars across the sky and measuring how they move, astronomers can test models of the galaxy's unseen mass. Some streams wrap around large portions of the sky, giving a broad view of the halo's pull over immense distances. Others are narrower or more local, but still sensitive to the dark gravitational landscape. The outer halo, which seems empty at first glance, becomes full of quiet lines that reveal the shape of the invisible. Globular clusters also help. These are old, dense groups of stars that orbit the Milky Way far beyond the main disk. Because they are compact and bright enough to be followed at large distances, they serve as long-lived traces of the galaxy's outer gravitational field. Their speeds and orbital paths help estimate the total mass enclosed within their distances. A single cluster does not define the whole halo, but many such objects together provide a wider map. They show that the Milky Way remains massive far beyond the bright regions that dominate ordinary sight. Other distant halo stars add more detail. Some are giant stars bright enough to be seen at very large distances. Others are variable stars whose intrinsic brightness can be estimated, allowing their distances to be measured more reliably. When these stars are placed into three-dimensional maps and their motions are combined with modern astrometric data, the structure of the halo becomes clearer. The outer Milky Way is not a smooth fog of stars. It contains shells, streams, overdensities, and lingering traces of past growth. All of these move within the dark matter halo, and their arrangement offers clues to its extent and form. This work has advanced greatly through modern sky surveys and precision measurements of stellar motion. The halo can now be mapped not just as a static region of faint stars, but as a dynamic structure. Distances, proper motions across the sky, and velocities along the line of sight together allow astronomers to reconstruct orbits with far greater confidence than before. From these data, the Milky Way appears as a galaxy embedded in a very extended dark matter halo, whose mass far exceeds that of its visible stars and gas. The exact total mass remains uncertain within a range, because the outermost parts are difficult to sample completely. But the broad conclusion is stable. The galaxy is much heavier than its light suggests. The shape of the Milky Way halo is also an active question. A perfectly spherical halo would be mathematically simple, but the real galaxy is unlikely to be so exact. Stellar streams and other traces suggest that the halo may be somewhat flattened or elongated in certain regions, and perhaps not identical in shape at all distances. The influence of past mergers, the pull of the visible disk, and the continuing assembly of the galaxy can all leave subtle marks on the halo's structure. Even so, the outer halo is clearly not confined to the flat plane of the Milky Way's bright band. It surrounds the galaxy in a much broader form, holding distant traces in long orbits through a mostly unseen mass field. This region also reveals the Milky Way as a growing system rather than a finished object. The outer halo contains the remains of earlier accretion, meaning the gradual gathering of smaller systems into a larger one. Streams are evidence of this. So are some of the unusual distributions of halo stars. The dark matter halo provides the large gravitational basin in which this assembly takes place. It holds the remnants of the past and continues to define the conditions under which the galaxy evolves. The outer halo is therefore both a present structure and a historical record. What makes the Milky Way's outer halo especially important in the story of dark matter is its intimacy. The dark halo of a distant galaxy can be inferred in broad terms from its rotation and lensing. The halo of the Milky Way can be studied through individual stars and streams, each one moving through the unseen field of the galaxy that contains the solar system itself. The problem of dark matter becomes local in a cosmic sense. The galaxy around Earth is not merely surrounded by darkness in a poetic way. It is embedded in a real and extended dark mass distribution that governs the motions of objects far beyond the shining disk. So this seventh region inward is the spacious outer halo of the Milky Way, where faint stars, globular clusters, and stellar streams act as quiet guides through a vast invisible domain. From inside the galaxy, astronomers trace the reach of its mass by following these distant markers across the sky. Their motions show that the Milky Way extends far beyond its bright band of starlight and that most of its matter remains unseen. The outer halo is wide, sparse, and difficult to view directly, but it steadily reveals the deep dark structure of the home galaxy. Around large galaxies, the dark halo does not remain empty of companions. It contains smaller systems that move within the larger gravitational field and reveal its depth in a more delicate way. These companions are satellite galaxies. Many are dwarf galaxies, meaning systems much smaller and fainter than a major spiral or elliptical galaxy. Some hold only a modest number of stars and very little gas. Some are so faint that they are difficult to notice at all against the sky. Yet these modest objects have become some of the most valuable places for studying dark matter, because their visible matter is sparse while their motions suggest a much larger unseen mass. A dwarf satellite galaxy can seem almost insubstantial in ordinary light. It may contain only old stars, with no bright spiral arms, no large gas disk, and no strong ongoing star formation. In visible appearance, it can resemble a loose and dim cloud of stars rather than a richly structured galaxy. But the weakness of its light is part of what makes it useful. If the visible component is small, then the effect of any unseen mass becomes easier to isolate. The stars in such a galaxy move under the pull of the system's total gravity. When their speeds are measured, they often indicate that the dwarf is much heavier than its starlight would imply. This contrast is especially strong in the faint dwarf satellites of the Milky Way and the Andromeda Galaxy. These small companions are close enough for individual stars to be studied in detail. Astronomers can measure how fast those stars move within the dwarf system. If the stars alone supplied most of the mass, then the measured internal motions would be modest, because there would not be much gravity to hold faster motion in place. But many dwarf satellites show velocity dispersions, meaning a spread of stellar speeds, that are too large for their visible stars alone. The simplest interpretation is that they are embedded in dense dark matter halos. What makes these systems striking is the ratio between light and mass. In a large spiral galaxy, the visible disk and bulge still contribute a significant share of the gravity in the bright inner regions. In a faint dwarf satellite, the visible stars may contribute only a small fraction of the total inferred mass. The galaxy then appears dark matter dominated almost throughout. This does not mean it contains no ordinary matter. The stars are real and measurable, and in some cases traces of gas are present or once were present, but the dominant mass seems to belong to an unseen component. In quiet observational terms, these are places where dark matter appears to outweigh starlight by a very wide margin. Because of this, dwarf satellites are often described as natural laboratories for dark matter. The phrase does not mean they are simple. They are affected by tidal forces from their larger host galaxy, and some have complex histories of gas loss, star formation, and disruption. But they are useful because they place dark matter in a setting where ordinary luminous structure is minimal. Their small size and faintness make them sensitive to how dark matter gathers on relatively small scales. In that sense, they test whether the standard dark matter picture works not only for clusters and giant galaxies, but also for the smallest galactic systems that can survive. These satellites also help map the larger halo of the host galaxy. Their orbits respond to the host's total mass distribution, while their internal motions reveal their own local dark matter content. A dwarf satellite is therefore both a companion and a probe. It moves within the dark halo of the larger galaxy, and at the same time it may carry a dense halo of its own. This layered arrangement is important. It shows dark matter not only as one enormous envelope around a major galaxy, but as a structure that can gather into nested systems, with smaller halos existing inside larger ones. The faintest dwarf satellites are especially interesting because they challenge intuition about what counts as a galaxy. Some contain so few stars that, at first glance, they might seem closer to star clusters than to galaxies. The distinction comes from gravity and mass content. A star cluster is usually held together by the gravity of its stars alone. A dwarf galaxy, even a very faint one, appears to require much more mass than its stars can provide. Its stars move as though they inhabit a deeper gravitational well. That deeper well is what makes it a galaxy in the dark matter sense. It is not the richness of its light, but the hidden mass underlying it. These systems have also sharpened several puzzles in the dark matter picture. Computer simulations of cold, dark matter often predict large numbers of small subhalos, meaning smaller clumps of dark matter orbiting within a larger halo. For a time, the number of observed dwarf satellites around the Milky Way seemed smaller than expected. This became known as the missing satellites problem. Over time, as deeper surveys revealed many more faint dwarf galaxies, the discrepancy became less severe, though it did not vanish in every detail. The issue now depends strongly on how stars form inefficiently in very small halos, and how many such systems remain too faint to detect. The puzzle, therefore, becomes not a simple contradiction, but a test of how dark matter and galaxy formation work together on the smallest scales. Another difficulty appears in the inner density structure of some dwarf galaxies. The simplest cold dark matter simulations tend to produce dense central cusps, meaning sharply rising densities toward the center. Observations of some small galaxies, especially those outside the strongest tidal influence of large hosts, sometimes suggest flatter central distributions, more like cores than cusps. This has led to continuing debate. Some researchers argue that ordinary processes such as repeated bursts of star formation and gas outflow can reshape the inner distribution of matter. Others explore whether the dark matter itself may have richer properties than the simplest collisionless model assumes. In this way, dwarf galaxies do not only support the existence of dark matter, they also test how strange it may need to be. The environment of a large host galaxy can complicate these systems further. As a dwarf satellite orbits, tidal forces can stretch it, strip stars from its outskirts, and remove some of its dark matter. Gas can also be lost through interaction with the host's surrounding medium. The result is that a present-day dwarf satellite may not be a pristine object. It may be the remnant of a system once larger and richer. Even so, its surviving stars still carry information about the mass that remains, and its current state still reflects the underlying role of dark matter in keeping the system bound as long as it does. At this inward stage of the subject, the scale has narrowed from great halos and outer streams to the small companion realms within them. These faint galaxies are easy to overlook in light and hard to dismiss in gravity. They carry little shine, yet often require substantial unseen mass. They orbit inside the larger dark domain of their host, while also preserving smaller dark domains of their own. Their quiet motions and sparse starlight make them some of the clearest small-scale witnesses to the hidden mass of the universe. Inside a dark matter halo, the question is no longer only whether extra mass exists. It becomes a question about shape and concentration. How does that unseen mass arrange itself toward the inner regions of a galaxy? Does it rise steeply toward the center, or does it level into a broader and gentler core? This is one of the places where dark matter begins to seem stranger than a single straightforward answer. On large scales, the standard cold dark matter picture describes cosmic structure with great success. In the inner parts of some halos, especially in smaller galaxies, observations and simple expectations do not always align so neatly. In the language of structure, a cusp means a sharply increasing central density. As one moves inward, the amount of dark matter per unit volume rises quickly. A core means a flatter central distribution, where the density levels off instead of climbing steeply. This difference matters because it affects how stars and gas move near the center of a galaxy. A cusp produces one kind of gravitational pattern, a core produces another. When astronomers compare measured inner motions with theoretical expectations, they try to determine which sort of inner mass profile is more consistent with the data. The simplest cold, dark matter simulations, especially those that include only dark matter and gravity, tend to form halos with cuspy centers. This result appears naturally when many small dark matter clumps merge and settle into larger structures over cosmic time. In that picture, the inner halo becomes dense toward the center. For large-scale cosmology, this behavior is not a problem. But when the prediction is compared with the observed inner motions of some dwarf galaxies and low-surface brightness galaxies, meaning galaxies whose stars are spread thinly and shine weakly per unit area, the observed behavior can look smoother than a steep cusp would suggest. In these systems, the central gravitational pull often seems more compatible with a core. This tension is known as the core cusp problem. It is not a universal verdict applying equally to every galaxy. Some systems are difficult to measure cleanly. Some can be interpreted in more than one way, depending on assumptions about geometry, gas motion, or stellar mass. Yet the repeated appearance of apparently shallow central densities in certain galaxies has been important for dark matter research. It raises the possibility that either the simplest simulations are missing crucial ordinary physics, or the dark matter itself may behave in a richer way than the most basic cold collisionless model assumes. Ordinary matter can complicate the inner regions of galaxies much more than the simplest dark matter only simulations allow. Gas can cool and flow inward. Stars can form in concentrated bursts. Massive stars can inject energy into their surroundings when they die, driving gas outward and changing the gravitational potential in rapid episodes. Over many cycles, these repeated changes can stir the central distribution of matter and potentially transform a cusp into a flatter core. In this view, the apparent disagreement is not necessarily a failure of dark matter, but a sign that the inner life of galaxies matters. The dark halo is not isolated from the luminous material. It responds to the history of gas and stars moving within it. This explanation appears especially plausible in galaxies where enough ordinary matter exists to reshape the inner potential, but it becomes less secure in systems that are extremely faint and apparently dominated by dark matter from the start. There, the amount of stellar activity may seem too limited to have strongly altered the central halo. If such galaxies still show clear cores, the case for richer dark matter physics becomes stronger. This is one reason the smallest and faintest galaxies remain so important. Their very simplicity may help reveal whether the central tension is created by ordinary processes or by the deeper properties of the dark matter itself. the problem is made harder by observation. The inner regions of galaxies are not always easy to measure precisely. Gas can show non-circular motions. Bars and asymmetries can disturb the simple picture of smooth rotation. Stellar velocity measurements carry uncertainties and depend on assumptions about orbital structure, inclination, resolution, and the thickness of the disk can all affect how the central mass profile is inferred. For this reason, the core cusp problem is not a clean contradiction with one simple numerical answer. It is a persistent pattern of tension emerging from many studies, especially in certain classes of galaxies. Another related issue concerns the number and density of the largest subhalos predicted around a galaxy like the Milky Way. Some simulations suggest that the most massive of these subhalos should be dense enough to host visible dwarf galaxies, yet the observed brightest satellites do not always appear to match those densest expected structures. This difficulty becomes known as the too big to fail problem, meaning that some predicted subhalos seem too massive and dense to have failed at making observable galaxies. Here too, the tension may be reduced when ordinary processes such as stellar feedback, tidal stripping, and a more complete observational census are included. But the puzzle has encouraged broader thinking about the inner behavior of dark matter halos. These inner tensions do not erase the large-scale success of dark matter. The standard cold model still describes the cosmic microwave background, large-scale structure, and many gravitational observations with impressive consistency. The challenge lies in the transition from grand scales to small inner regions where galaxy formation becomes messy and where subtle details of the dark matter distribution matter greatly. This is why dark matter may be stranger than first thought, not because the evidence for it disappears, but because the simplest version of it may not be enough to explain every observed interior. Several possibilities remain under active study. One possibility is that better treatment of ordinary matter will resolve much of the tension. In this case, the dark matter remains cold and nearly collisionless, but its halos are reshaped by the visible matter they help host. Another possibility is that dark matter particles interact weakly with one another, smoothing the central density and producing cores more naturally. Yet another is that the relevant dark matter particle may be lighter or dynamically different from the standard cold picture, altering structure on small scales. Modified gravity ideas also continue to be tested in these contexts, though they must still face the broader evidence from clusters and cosmology. At this inward level, the main scientific focus is the central architecture of halos. The question is not whether halos exist, but how their hidden mass is packed inside. The answer matters because inner structure connects cosmic theory to the fine details of real galaxies. A dark halo that is too steep, too dense, too clumpy, or not clumpy enough will leave traces in the motions of stars and gas. The inner regions therefore act as a demanding test, one that forces theory to meet observation at smaller and more sensitive scales. So this ninth region inward is the halo interior, where the broad certainty of unseen mass gives way to a subtler issue of distribution. Some galaxies seem to prefer smoother cores where the simplest cold dark matter model first expects cusps. The disagreement may reflect the influence of ordinary matter, the richer behavior of dark matter, or a combination of both. In these quiet central regions, the subject becomes more intricate. The dark matter does not vanish. It becomes more detailed, and therefore more strange. Beneath the observed shapes of halos and the tensions in their inner regions lies the standard working picture of dark matter itself. In this picture, dark matter is cold and nearly collisionless. Cold does not mean cold in the everyday sense of temperature felt by skin or measured in weather. Here it means that the dark matter moves slowly compared with the speed of light during the era when cosmic structures begin to grow. Nearly collisionless means that dark matter particles, if they are particles, interact very weakly with one another and with ordinary matter, apart from gravity. These two properties together form the baseline description that has guided much of modern cosmology. This description matters because it is simple enough to calculate and powerful enough to explain a great deal. If dark matter moves slowly in the early universe, then small density variations are not easily washed away by rapid motion. They can survive and grow under gravity. If dark matter is nearly collisionless, then it does not clump and shock in the same way as ordinary gas. It does not radiate energy away through light. It does not cool into thin disks. It does not become compressed by ordinary pressure. Instead, it remains in broad halos and streams, responding mainly to gravity over long spans of time. These properties help explain why dark matter forms extended structures while stars and gas occupy more concentrated luminous regions inside them. The word cold is especially important in the history of cosmic structure. In the early universe, tiny differences in density exist from place to place. Over time, gravity strengthens the denser regions by drawing in more matter. If the dominant unseen matter were moving too quickly, then those small differences on small scales would be blurred out before they could grow. A cold, dark matter component avoids that problem. It allows small structures to form first, later merging into larger ones. This bottom-up growth becomes one of the characteristic features of the standard cosmological model. Large halos are built gradually from many smaller pieces, and the cosmic web emerges naturally from this process. The word collisionless is equally important. Ordinary matter does many things. Dark matter does not appear to do. Gas clouds collide, compress, heat, cool, and sometimes form stars. Dust grains absorb and scatter light. Plasma responds to electromagnetic forces. Dark matter in the standard picture largely avoids this rich physical behavior. It does not stick, glow, cool, or dissipate energy in familiar ways. Because of that, when dark matter gathers into a halo, it does not collapse into the thin rotating disk seen in a spiral galaxy. It remains more spread out, filling a larger volume around the visible galaxy. This is why the standard model naturally produces large dark halos instead of bright compact structures. This baseline picture also explains why dark matter is so difficult to detect directly. If it interacts only very weakly with ordinary matter, then it passes through stars, planets, gas clouds, and detectors with little effect. Gravity reveals that it is present, but laboratory detection becomes extremely hard. The standard picture does not require that dark matter have absolutely no non-gravitational interactions. It requires only that any such interactions be weak enough to have escaped clear detection so far and rare enough not to disrupt the successful large-scale behavior seen in cosmology. In practice, this makes dark matter elusive. It can dominate the mass of a galaxy while remaining invisible to all ordinary telescopes. Computer simulations built on this cold and nearly collisionless picture have achieved some of the most important successes in cosmology. Starting from the slight density variations inferred from the early relic radiation, they produce a universe in which matter gathers into filaments, halos, and clusters with the distribution that resembles the observed large-scale structure. Galaxies form within the densest parts of dark matter halos. Clusters grow at the intersections of filaments. The broad cosmic web appears with the right kind of hierarchy and contrast. This success is one reason the baseline picture remains so influential. It does not answer every detail, but it describes the larger structures with remarkable strength. The same framework also helps explain why galaxies are surrounded by halos rather than ending where the light ends. In a cold, collisionless model, dark matter falls into gravitational wells and settles into extended distributions shaped by cosmic growth and repeated mergers. Since it does not lose energy through radiation, it cannot collapse inward as efficiently as ordinary gas. The result is a diffuse but massive halo. Ordinary matter later cools within this halo, sinks deeper, and forms stars in a more compact region. The visible galaxy therefore becomes a bright interior feature inside a larger dark structure. This arrangement follows naturally from the different physical behavior of the two components. At the same time, the standard picture is not a final statement about essence. It is a phenomenological model, meaning a model defined by observed behavior rather than by a confirmed underlying identity. It says that the dominant unseen matter behaves as though it is cold and nearly collisionless. It does not yet prove what the particle is, whether there is one particle or several, or whether the deeper dark sector has hidden complexity. The strength of the model lies in what it explains, not in a completed microscopic description. This distinction matters because one can have a successful large-scale framework without yet knowing the full inner nature of the substance involved. That is why the cold, collisionless model functions as a baseline rather than as an unquestionable endpoint. It is the simplest description that fits a wide range of observations. When astronomers and physicists speak of tensions or anomalies on smaller scales, they are usually comparing the data against this baseline. The question is whether the standard picture remains sufficient once the ordinary physics of stars and gas is treated carefully, or whether dark matter must possess additional properties beyond this minimal set. But the starting point is clear. Before one adds richness, one begins with the model that already works across most of the visible cosmic landscape. This inward layer of the subject is therefore a conceptual one. After moving from the universe as a whole through webs, clusters, halos, disks, streams, satellites, and inner density tensions, the focus now rests on the underlying behavior assumed for the unseen matter itself. Cold means slow enough to preserve small-scale seeds of structure. Nearly collisionless means largely governed by gravity rather than by strong scattering, cooling, or radiation. These two ideas are modest in wording, yet vast in consequence. They allow an invisible substance to shape the architecture of the cosmos without ever becoming part of the bright astronomical scenery. So this 10th region inward is the standard dark matter assumption at its calmest and clearest. It is not yet a detailed particle theory. It is a behavioral portrait. The unseen matter moves slowly enough to help build structure from the bottom upward, and it interacts weakly enough to remain broad, dark, and difficult to catch. From this simple baseline, much of modern cosmology has been constructed, and from this same baseline, the deeper question begins to sharpen. If dark matter is real, is this quiet description all that it is, or only the outer surface of something stranger still? If the standard picture describes dark matter as cold and nearly collisionless, then the next inward step is to relax part of that description without abandoning the larger framework. In this view, dark matter still exists as a real unseen component that outweighs ordinary matter in galaxies and clusters. But it is not entirely indifferent to itself. Its particles, if they are particles, may occasionally scatter from one another. This idea is called self-interacting dark matter. The phrase means that dark matter can have non-gravitational interactions within the dark sector itself, while still remaining extremely difficult to detect through ordinary light or ordinary matter. At this level, dark matter begins to seem stranger, because it is no longer only passive mass. It may have a hidden internal life. The attraction of this idea comes from the inner behavior of halos. In the simplest collisionless model, dark matter particles pass through one another almost freely, so the central regions of halos can remain sharply concentrated. But if dark matter particles scatter from one another often enough, then they can exchange energy and momentum inside the halo. Over long spans of time, this can soften the central density and make the inner profile rounder and less steep. In plain terms, self-interaction can turn a sharply peaked center into a gentler one. This is why the idea becomes especially interesting in galaxies, whose observed inner mass distribution appears smoother than the simplest collisionless model first predicts. The basic physical picture is calm and gradual. In a dense inner halo, dark matter particles move through a crowded gravitational environment. If they never scatter, the inner structure is shaped only by gravity and the accumulated history of cosmic assembly. If they do scatter occasionally, then the central region can begin to redistribute energy internally. Some particles lose energy and sink inward, others gain energy and move outward. The net effect over time can resemble thermal relaxation, meaning a tendency for the system to smooth differences in the way energy is distributed. This does not make dark matter behave like ordinary glowing gas. It still does not cool by radiation or collapse into a bright disk. But it does become less rigidly collisionless than the standard baseline assumes. This possibility is important because it offers a natural way to create cores in some galaxies. A self-interacting halo can develop a central region with a flatter density profile without requiring all such smoothing to come from the action of stars and gas alone. In dwarf galaxies, where the visible matter may be sparse, this is especially appealing. The hidden mass itself can help explain why the inner density appears gentler. The halo then becomes not just a container for visible matter, but a medium with its own weak but meaningful internal dynamics. The idea also affects shape. In the collisionless picture, halos formed through mergers and anisotropic infall can retain noticeable elongation or triaxiality, meaning three unequal principal directions. If self-interactions are present, repeated scattering tends to make the inner halo rounder over time, especially where density is high and interactions are more common. This offers another observational clue. The central regions of galaxies and clusters may carry hints of whether dark matter has been freely streaming through itself or slowly smoothing its own structure from within. In this way, self-interacting dark matter is not only about core formation, it is also about the geometry of hidden mass. Yet the interactions cannot be too strong. Galaxy clusters place powerful limits on that. In collisions between clusters, the dominant gravitating mass appears to pass through with relatively little drag compared with the hot ordinary gas. If dark matter scattered too readily, the mass distribution in those collisions would be altered more strongly. The same concern applies to the overall survival and shape of halos. Dark matter must remain dark and mostly non-dissipative on large scales, or the successful large-scale picture would begin to break. Self-interacting dark matter therefore occupies an intermediate space. It is not fully collisionless, but neither is it strongly collisional like ordinary gas. This balance has led researchers to explore interactions that depend on speed. In simple language, the scattering may be more effective in the slow environments of dwarf galaxies and less effective in the fast environments of galaxy clusters. Such velocity-dependent behavior is attractive because it allows self-interactions to matter where inner halo tensions are strongest, while remaining subtle where cluster observations impose tight constraints. If this is correct, then dark matter would not behave in one identical way across all cosmic settings. Its hidden interactions would reveal themselves differently depending on the scale and dynamical environment. That possibility makes dark matter seem more like a complex physical substance and less like a single fixed correction term. The notion of self-interaction also opens the door to a broader hidden sector. In ordinary matter, richness comes from forces and composite structures. Atoms form from charged particles interacting through electromagnetism. Nuclei form through the strong force. By contrast, the simplest cold dark matter picture gives dark matter almost no comparable internal story. Self-interacting models suggest that the dark sector may have at least a faint version of such structure. There may be a mediator, meaning a particle or field that carries the interaction between dark matter particles. There may be resonances, preferred scattering conditions, or behavior that changes with speed and density. None of this is established, but the idea moves dark matter away from utter simplicity. Even so, the evidence remains indirect. No laboratory has yet isolated a dark matter self-interaction. No telescope sees dark matter colliding in a visible flash. The case is built through astrophysical consequences, smoother cores, altered halo shapes, limits from merging clusters, and the statistical behavior of structure across different scales. This makes the subject both promising and difficult. A self-interaction strong enough to affect halo interiors may still be far too weak to reveal itself easily in conventional experiments. The dark sector could be quietly active while remaining almost inaccessible to direct observation. This inward region of the topic therefore changes the character of the dark matter problem. In the earlier baseline picture, dark matter acts almost like a silent gravitational background, shaping halos while doing little else. With self-interactions, the hidden matter begins to behave as a system with internal processes. It can exchange momentum, redistribute energy, and modify its own central structure. These effects are subtle rather than dramatic, but they matter because they connect the largest cosmological framework to the smaller, more detailed behavior of real galaxies. The idea is scientifically conservative in one sense and adventurous in another. It is conservative because it keeps the great successes of dark matter on cosmic scales. It does not discard halos, clusters, lensing, or the growth of structure. It accepts that most matter is unseen and gravitationally real. But it is adventurous because it allows the unseen matter to possess additional physical properties beyond the minimum. It says that the dark universe may not be governed by one perfectly mute substance. It may contain matter that speaks softly to itself. So this 11th region inward is the hidden interaction within the hidden mass. Dark matter remains dark, extended, and dominant in gravity. But it may not be entirely collisionless after all. In dense halo interiors, weak self-scattering can smooth central structure, alter shape, and help explain why some galaxies look gentler in their cores than the simplest model first suggests. The change is small in description, yet deep in meaning. The unseen matter may be stranger not because it vanishes under scrutiny, but because closer study gives it more behavior than expected. Another way to make dark matter stranger than the simplest picture suggests is not to change how strongly it interacts, but to change how swiftly it moves in the early universe. In the standard cold model, dark matter moves slowly enough for very small density variations to survive and grow. In a warmer picture, the dark matter is lighter or faster in the young cosmos, and that extra motion smooths away some of the smallest primordial structure before gravity can amplify it. This idea is called warm dark matter. The word warm does not describe ordinary temperature in the everyday sense. It describes a middle behavior between cold dark matter, which moves slowly enough to preserve very small structure, and hot dark matter, which moves so quickly that too much small structure is erased. Warm dark matter therefore changes the inner story of dark matter by changing its early motion. The key process is called free streaming. Free streaming means motion that carries particles out of small dense regions before gravity has time to hold them together. In the early universe, when the cosmos is denser and younger, the speed of dark matter matters greatly. If the particles move very little, small clumps can remain and later grow into small halos. If they move more quickly, then the smallest irregularities are blurred out. They are smoothed into larger scale uniformity before they can become distinct gravitational seeds. Warm dark matter is interesting because it allows this smoothing to happen on small scales, while still preserving the larger structures of the cosmic web, galaxy clusters, and large galaxies. This matters because some of the tensions in dark matter appear most strongly on small scales. The number of predicted small subhalos, the dense inner structure of dwarf galaxies, and the abundance of tiny clumps all depend on how much small-scale structure survives from the early universe into later cosmic history. If warm dark matter removes some of the smallest seeds at the beginning, then fewer very small halos form later. The population of faint satellites can be reduced. The smallest structures become less crowded and less sharply concentrated. In this way, warmth offers a different route to a smoother, small-scale universe than self-interaction does. Self-interaction changes halo behavior after halos form. Warmth changes which small halos can form in the first place. The physical picture is quiet but profound. In a cold model, structure grows hierarchically from many small units. Small clumps appear early and later merge into larger systems. In a warm model, the very smallest clumps never fully emerge, because the early motion of the dark matter wipes out their seeds. The hierarchy remains, but its lower end is trimmed away. Large structure still forms, galaxies still gather in halos, the cosmic web still appears. Yet the fine-grained texture of the dark universe becomes smoother. There are fewer small building blocks, and this changes the later details of halo growth. Warm dark matter has therefore drawn attention as a possible explanation for some of the small-scale puzzles that arise in the simplest cold model. If there are fewer tiny halos, then the missing satellite's tension can be reduced without requiring every predicted small halo to have failed invisibly at forming stars. If the inner assembly of halos is gentler, then central densities may also be somewhat reduced in certain systems. These are attractive features. They show that a modest change in the early motion of the dark matter can propagate forward into differences that astronomers might observe in the present-day universe. Yet this idea is tightly constrained by observation. The dark matter cannot be too warm, or it would erase too much small-scale structure. The universe contains many small galaxies, many early forming systems, and a rich pattern of matter on scales that would be overly suppressed if the dominant unseen matter had moved too rapidly in the early cosmos. One of the strongest tests comes from the distribution of hydrogen gas seen in the absorption patterns of distant quasar light, often called the Lyman alpha forest. These fine variations trace matter structure on relatively small scales at early times. They generally favour dark matter that is cold or only mildly warm. This means warm dark matter remains possible in some forms, but it cannot wander too far from the cold baseline without conflicting with what the young structured universe appears to contain. Because of this, warm dark matter is usually explored as a narrow modification rather than a complete overthrow of the standard picture. It offers some smoothing at small scales, but not so much that large-scale success is lost. The candidate particles are often imagined as lighter than the heavy particles first considered in many cold dark matter searches. One widely discussed example is a sterile neutrino, a hypothetical particle related in concept to ordinary neutrinos, but not participating in the usual weak interaction in the same way. Such particles remain unconfirmed, and the allowed ranges of their properties are increasingly constrained by astronomical data and laboratory searches. Still, they illustrate how the inner nature of dark matter can shift from one family of possibilities to another without changing the broad observation that unseen mass dominates. Warm dark matter also changes the timing of structure formation. If small-scale seeds are suppressed, then the first small halos appear later, and the early growth of galaxies can be delayed or altered. This does not mean galaxies fail to form. It means the sequence of assembly becomes smoother at the lower end. The earliest dwarf-like systems may be rarer. The smallest substructure inside larger halos may be reduced. These differences matter because the history of the first galaxies, reionization, and faint satellite populations all depend on how structure emerges from the initial cosmic conditions. In this sense, early motion leaves a long memory. There is also a conceptual appeal to warm dark matter. It shows that dark matter need not become stranger only by adding hidden forces or self-scattering. It can become stranger simply by being lighter and more mobile than once assumed. The unseen matter then remains mostly passive in interaction, yet active in another sense through its motion in the early universe. Its behavior is changed not by extra complexity in its present-day halos, but by a different inheritance from the hot beginning. This shifts attention from the centers of galaxies back to the first stages of structure growth, where tiny initial patterns either survive or disappear. Still, the limits are important. Warm dark matter is not a free solution to every small-scale issue, in many cases. Ordinary processes involving gas, stars, and feedback can also alter small galaxies, and these effects must be considered carefully before attributing differences to the dark matter alone. Observations increasingly suggest that if the dominant dark matter is warm, it must be only mildly so. The broad cosmic picture remains close to the cold standard. The room for warmth exists, but it is measured and narrow. So this 12th region inward is the early motion of the unseen matter itself. Dark matter may be lighter and faster than the simplest cold picture assumes, and that early motion may smooth away the smallest seeds of a later structure. The result is a universe whose broad framework remains intact, but whose fine dark texture becomes less crowded and less sharp. In this quieter, swifter version of the dark sector, the strangeness lies not in hidden collisions, but in the ancient velocity of matter that never shines. Deeper within the possible nature of dark matter lies an idea that changes not only its motion or its interactions, but the very way it is described. In this view, dark matter is so light that it does not behave primarily as a collection of separate, localized particles on galactic scales. Instead, it behaves as a coherent wave-like field spread across large distances. This possibility is often called ultralight dark matter or fuzzy dark matter. The word fuzzy does not mean uncertain in a casual sense. It refers to the fact that the dark matter would have a wavelength large enough to matter inside galaxies, giving the hidden mass a blurred, wave-shaped character rather than a purely granular particle one. The reason this becomes possible is simple in principle. Every form of matter has wave properties in quantum theory. For ordinary heavy objects, these wavelengths are far too small to matter in astronomy. For an extremely light dark matter particle, however, the associated wavelength can become enormous on galactic scales. If the mass is tiny enough, and if the occupation number is very large, then the dark matter is better described as a classical field with a coherent wave pattern than as a sparse swarm of separate particles. On very large cosmic scales, this wave-like matter can still resemble cold dark matter quite closely, but on smaller scales, especially inside galaxies, its wave nature begins to leave visible gravitational consequences. One of the central effects is often described as quantum pressure. The phrase is a shorthand for the tendency of a wave-like system to resist being squeezed into an arbitrarily small region. In practical terms, this means ultralight dark matter does not pile up in the center of a halo as sharply as ordinary cold collisionless dark matter might. The wave nature smooths the matter distribution below a certain scale. It does not remove gravity. It changes how tightly gravity can concentrate the hidden mass. This makes the idea attractive in galaxies whose inner regions appear gentler and less sharply peaked than the simplest cold dark matter expectation. In this picture, the center of a halo can develop a solitonic core. A soliton is a stable wave configuration that holds its shape while being supported by a balance between gravity pulling inward and wave effects resisting overcompression. In plain language, the central dark matter distribution becomes a smooth wave-supported lump rather than a steep cusp. Around that central core, the halo continues outward into a broader structure that can resemble an ordinary halo at larger radii. The resulting galaxy then contains two linked regimes, a wave-supported inner core and a more extended outer halo, where the dark matter behaves more like the familiar cold case in its overall gravitational role. This is one reason wave-like dark matter has drawn attention in the study of dwarf galaxies and low surface brightness galaxies. If the central regions of such systems are smoother than the simplest cold model predicts, then a wave-supported core offers one natural explanation. The smoothing does not require strong dark matter self-collisions. It arises from the very light mass and extended wavelength of the dark matter field itself. In that sense, the strangeness here is more fundamental. The dark matter is not merely a weakly interacting substance with hidden collisions. It may be matter whose basic astronomical form is field-like and wave-like. Another important consequence appears during structure formation. Because the wave nature resists compression on small scales, very small halos form less easily. This resembles the suppression of small structure found in warm dark matter. But the physical origin is different. Warm dark matter smooths the early universe because faster particles free stream out of small fluctuations. Wave-like dark matter smooths it because the field resists being packed into structures below a certain characteristic scale. The result is again a less crowded small-scale universe, with fewer tiny halos and smoother inner structures. Large-scale cosmic structure can remain broadly intact, but the fine texture of the dark universe becomes altered. The halo itself also becomes more dynamic in an unusual way. In ordinary particle-based descriptions, one imagines many individual particles orbiting through a potential. In a wave-like halo, interference patterns can arise as different parts of the field overlap. This can create fluctuating density granules on certain scales, not as permanent objects, but as temporary patterns of constructive and destructive interference. The dark halo then becomes not entirely smooth and not entirely particulate. It becomes a restless wave environment, with density patterns that shimmer and shift through time while still producing the broad gravitational effect of a halo. This is an unfamiliar kind of matter compared with ordinary astronomical intuition. Such fluctuations may have observable consequences. In principle, they can gently heat stellar populations or disturb delicate structures such as thin stellar streams if the fluctuations are strong enough and act over long times. The central solitonic core can also affect rotation curves and the motions of stars near galactic centers. These possibilities make wave-like dark matter testable through astrophysical structure rather than only through laboratory experiments. The field does not shine. It still reveals itself by the kinds of halos it builds, the smoothness of their centers, the abundance of small galaxies, and the subtle long-term stirring it may cause in stars moving through it. At the same time, the idea is now tightly constrained. For the wave effects to matter on galactic scales, the dark matter must be extremely light, but observations of small-scale structure, the abundance of subhalos, the Lyman alpha forest, and galactic dynamics place increasing pressure on the simplest version in which one ultralight field makes up all of the dark matter. In recent years, the allowed space for the classic fuzzy dark matter picture has narrowed considerably. This does not mean all wave-like dark matter is ruled out. It means the simplest and most celebrated version faces strong observational limits. The wave may still exist, but perhaps only in a smaller role, at a somewhat different mass, or within a richer mixed dark sector. That is part of what makes this region inward so important. It shows how dark matter can become stranger without becoming less scientific. The proposal is concrete. It makes predictions. It can be simulated and compared with data. It preserves much of the large-scale success of dark matter, while changing the inner texture of halos and the survival of very small structures. Yet it is also constrained enough that it cannot simply be shaped at will to fit every anomaly. It must pass real tests, and many of those tests are now severe. Conceptually, wave-like dark matter changes the emotional center of the subject. The unseen mass is no longer only a hidden particle sea moving through galaxies. It becomes a vast, coherent field whose wavelength is large enough to sculpt galactic structure directly. A galaxy then sits not only in a dark halo, but in a dark wave. The halo center is held up by wave support. The outer regions carry interference patterns. The smallest structures are pruned by the inability of the field to gather too tightly. The hidden universe starts to resemble not a shadow copy of ordinary matter, but a different state of matter altogether. So this 13th region inward is the wave nature of the dark sector. Dark matter may be so light that quantum behavior rises to astronomical importance, smoothing halo centers, suppressing the tinier structures, and turning the hidden mass into a coherent field spread across galactic space. The idea remains under pressure from modern constraints, especially in its simplest form, but it endures as one of the clearest examples of how dark matter may be stranger than first imagined. The invisible matter may not only outweigh the stars, it may also obey a different large-scale mode of existence. At a still deeper level of possibility, dark matter no longer appears as one simple substance with one simple behavior. It begins to resemble a hidden world with its own internal variety. This idea is often described as a dark sector. The phrase means that dark matter may belong to a set of particles and forces that are mostly separate from ordinary matter and ordinary light. In the simplest dark matter picture, One imagines a single new particle or one dominant species that mainly adds gravity. In a dark sector picture, that hidden matter may instead possess a richer structure, with multiple ingredients, weak interactions among them, and perhaps even bound states that form unseen composite objects. The strangeness here lies not only in invisibility, but in hidden complexity. Ordinary matter is not simple at its deepest useful level. What appears as solid or fluid material in everyday life is built from atoms, and atoms are made from lighter particles bound together by forces. Chemistry, light, heat, and structure arise because ordinary matter contains both components and interactions. Dark matter, by contrast, is often introduced in minimal terms, as though it were one quiet substance added to the cosmic inventory. The dark sector idea asks whether that simplicity is only apparent. Perhaps the unseen matter is not one mute particle at all. Perhaps it is a population, with its own relationships, its own binding, and its own hidden forms. This possibility begins with a modest thought. Dark matter interacts so weakly with ordinary matter that direct detection has remained elusive. That weak connection to ordinary matter does not necessarily imply weakness within the dark sector itself. The dark particles may interact more readily among themselves than with atoms and light. They may have their own mediator particles, meaning carriers of force within the hidden world. They may scatter, bind, decay, or transform under rules that are difficult to notice from the bright side of the universe. To ordinary observation, such a sector would still appear dark. To itself, however, it might not be simple at all. One broad version of this idea is mirror matter. In that picture, the hidden sector contains a parallel set of particles corresponding in some way to the known particles of ordinary matter. The resemblance need not be exact in every model, but the underlying thought is that nature may possess a hidden duplication or partial echo of the visible particle world. If so, dark matter would not be one lonely substance. It would be part of an unseen family. Such mirror matter would remain difficult to detect if its connection to ordinary matter were extremely weak, perhaps limited mainly to gravity or to very faint mixing effects. Yet it could still have a rich internal organization on its own side. Another version is atomic dark matter, sometimes described informally as dark atoms. The phrase does not mean ordinary atoms concealed in shadow. It means hypothetical bound states formed from dark particles under a dark force, in loose analogy to how ordinary atoms form from ordinary charged particles under electromagnetism. If this exists, then some portion of dark matter could be composite. It would not be a single fundamental particle everywhere. It would be matter assembled into larger hidden units. These units would still be dark to ordinary telescopes if the dark force does not couple significantly to ordinary light, but their existence would make dark matter conceptually much closer to a hidden material world than to a single invisible dust. Composite dark matter changes the meaning of halos and structure. In the simplest, collisionless model, a halo is a vast population of freely moving particles held together by gravity. In a richer dark sector, the internal state of the dark matter might influence how it behaves inside halos. Bound states could alter scattering. Long-range dark forces could change how clumps form or how central densities evolve. Dissipative processes, meaning processes that allow the system to lose usable kinetic energy internally, might even occur in some models, though observations place strong limits on how much of the total dark matter can behave in this way. If too much dark matter cooled and collapsed efficiently, the large-scale dark halo structure would look very different from what is observed. This means the hidden sector may have complexity, but that complexity must remain compatible with the broad success of extended dark halos and cosmic structure. That balance is central. A rich dark sector cannot be imagined without restraint. The universe already provides strong evidence that most dark matter behaves in a broadly halo-forming, non-luminous, and largely non-dissipative way on large scales. So if hidden forces or composite states exist, they must either be weak, rare, limited to a subcomponent of the dark matter, or arranged in such a way that the large-scale structure remains close to the successful standard picture. This does not make the idea less interesting, it makes it more subtle. The dark world may be complex, but it cannot simply mirror all the visible complexity openly, or the sky would reveal different gravitational patterns than it does. One reason researchers consider such models seriously is that a hidden sector can naturally explain why dark matter remains so hard to detect directly. If dark particles mostly talk to one another and only barely to ordinary matter, then laboratory silence is not surprising. The absence of ordinary signals becomes part of the theory rather than a failure of expectation. At the same time, the hidden sector can produce new astrophysical behavior. Self-interactions may arise naturally. Small-scale structure can be altered. Dark acoustic effects in the early universe, meaning wave-like pressure effects within the dark fluid, may appear in some models. The dark matter then becomes not merely unseen mass, but a medium with its own early history. This richness also expands the meaning of what a particle search is trying to find. If dark matter is one particle, then the task is to identify that particle. If dark matter belongs to a hidden sector, the task becomes more like opening a sealed door onto an unfamiliar branch of nature. There may be multiple species, stable and unstable states, force carriers, and rare portals connecting the dark sector to ordinary matter. A portal in this context means a very weak interaction channel that allows the hidden world to influence or occasionally produce measurable effects in ordinary experiments. Such ideas remain hypothetical, but they are scientifically appealing because they connect cosmic evidence with the broader logic of particle physics, where simplicity at first glance often gives way to layered structure on closer study. Even so, no observation yet compels this richer picture over a simpler one. The evidence for dark matter itself remains much stronger than the evidence for any particular hidden sector model. Astronomers know with considerable confidence that unseen mass shapes galaxies and the larger universe. It remains uncertain whether that unseen mass is one fundamental particle. Many particles, wave-like fields, self-interacting species, composite objects, or some combination. Hidden sector models are therefore not established descriptions. They are structured possibilities, explored because the dark matter problem remains unsolved at its deepest level, and because nature has often proved more intricate than the first useful model suggests. So this 14th region inward is the hidden society of the dark world. Dark matter may not be one silent ingredient, but part of a broader unseen sector with its own particles, forces, and bound forms. Mirror matter, dark atoms, and composite structures all express the same deeper thought. The invisible mass of the universe may possess an inner organization unknown in ordinary astronomy. The large halos and cosmic scaffolding remain real, but inside that unseen framework there may lie a richer material order, dark not because it is empty of structure, but because its structure is almost entirely closed to light. At the deepest level of the dark matter problem, the subject becomes quieter and more exacting. After the broad cosmic census, the web of structure, the mass of clusters, the outer halos of galaxies, the motions of stars and gas, the small companion realms, the inner tensions of halos, and the many possible hidden behaviors of the dark sector. One central fact remains unchanged. Dark matter is strongly inferred through gravity, but its fundamental identity is still unknown. This unknown is not a small unfinished detail at the edge of an otherwise complete theory. It is the innermost point of the subject. Astronomy has learned a great deal about what the unseen mass does. It has not yet learned with confidence what the unseen mass is. This distinction matters. In science, one may know the effects of something long before knowing its substance. The planet Neptune is inferred from gravitational irregularities before it is seen. The neutrino is proposed to account for missing energy before it is detected. In the case of dark matter, however, the unknown has lasted far longer and reaches more deeply into the structure of nature. The gravitational evidence accumulates across scales, from galaxies to clusters to the largest patterns in the universe. Yet no experiment has conclusively revealed a dark matter particle. No detector has provided an accepted direct signal, and no theory has emerged as the single established microscopic answer. The outer evidence is strong. The inner identity remains open. Many leading possibilities have been studied for decades. Heavy, weakly interacting particles once seemed especially attractive because they fit naturally within some extensions of particle physics and could leave the right cosmic abundance after the early universe cooled. Lighter particles such as axions, originally proposed in another theoretical context, also became important candidates because they could be produced in the early cosmos and remain very difficult to detect. More recently, broader hidden sector possibilities, ultralight fields, self-interacting models, and composite dark matter ideas have expanded the landscape further. The field has not narrowed to one clear answer. In some respects, it has broadened. The longer the silence in experiments continues, the more seriously the strangeness of dark matter is taken. Direct detection experiments attempt to observe rare interactions between dark matter and ordinary matter in highly shielded instruments, often placed deep underground to reduce unwanted signals from ordinary cosmic particles. These experiments have become extraordinarily sensitive. They seek tiny energy deposits from an unseen particle passing through a detector and striking an atomic nucleus or an electron. Yet despite great refinement, they have not produced a universally accepted discovery. This absence does not rule out dark matter. It narrows the space in which certain kinds of dark matter can hide. It suggests that if dark matter interacts with ordinary matter beyond gravity, those interactions may be weaker, rarer, lighter, heavier, or stranger than many earlier models hoped. Collider experiments pursue the problem from another direction. Instead of waiting for dark matter to arrive from space, they try to create new particles in high-energy collisions. If dark matter particles are produced in such events, they may escape the detector without leaving direct tracks, showing their presence only through missing momentum or associated signals. So far, collider searches have also not delivered a confirmed dark matter discovery. This again does not erase the cosmological evidence. It means that the bridge between cosmic gravity and particle physics has not yet been crossed in a decisive way. The dark matter problem, therefore, remains suspended between astronomy and microphysics. Strongly real in one domain and elusive in the other, astronomical searches continue as well. Some dark matter candidates could decay or annihilate. meaning pairs of particles might destroy one another and produce ordinary particles such as gamma rays or other detectable byproducts. Telescopes search the sky for such signals, especially from regions expected to be rich in dark matter, such as the centers of galaxies or faint dwarf satellites. These searches have produced intriguing hints at times, but no signal has achieved lasting consensus as the long-sought signature of dark matter. The pattern repeats across methods. The gravitational presence is persistent. The direct identity remains withheld. This unresolved center is one reason some researchers continue to explore whether the evidence attributed to dark matter might instead reflect gravity behaving differently on very large or very weak acceleration scales. Modified gravity ideas have a long history, and some explain particular galactic regularities impressively well. More recent proposals continue to test whether additional fields, altered gravitational laws, or emergent effects could imitate some of what dark matter is supposed to do. These ideas are not a sign that the dark matter case has collapsed. They persist because the innermost identity remains unconfirmed, and because science tests alternatives whenever a central entity is inferred but not directly identified. Still, any such alternative faces a difficult burden. It must account not only for galaxy rotation, but also for cluster lensing, the separation seen in colliding clusters, the cosmic microwave background, and the growth of large-scale structure. That combination remains challenging to reproduce without some form of unseen matter. So the deepest region of the subject is not a settled particle resting at the bottom of explanation. It is a disciplined uncertainty. Observations indicate that something beyond ordinary matter shapes the universe gravitationally. It remains uncertain whether that something is one new particle, many particles, a field, a composite hidden medium, or a mixture of components. It also remains uncertain whether the final theory will preserve the current picture almost intact, or recast part of it in a deeper framework not yet known. The boundary between dark matter and modified gravity remains scientifically porous in the sense that comparison continues, even though the broad weight of present evidence favors an additional gravitating component. What makes dark matter stranger than first thought is not only that it fails to shine, it is that it has resisted simplification. The early expectation that one elegant particle might quickly solve the mystery has not been fulfilled. Instead, the problem has unfolded into layers. Large-scale cosmology supports the existence of unseen mass. Small-scale structure raises questions about its detailed behavior. Experiments constrain many once prominent candidates. New models multiply, then face new limits in turn. The hidden matter seems less like a single blank space waiting to be filled, and more like a sealed chamber whose door has been located but not opened. At this innermost point, science becomes patient. It does not treat uncertainty as failure. It treats uncertainty as the remaining shape of the truth. Dark matter may turn out to be a particle that was simply harder to find than expected. It may turn out to be a richer sector with hidden forces. It may involve ultralight fields, composite structures, or several components sharing the cosmic mass budget. Or part of the present framework may one day be revised by a deeper understanding of gravity itself. The current evidence does not justify choosing one of these with confidence. It justifies holding the center open. So this 15th and deepest region is the unresolved identity at the heart of the dark universe. The gravitational need for dark matter remains strong across the cosmos, but the nature of that unseen matter is still unconfirmed. Searches in laboratories, colliders, and the sky continue to narrow possibilities without yet selecting one. The great strangeness of dark matter lies here, in the gap between what the universe clearly does and what science can finally name. The invisible mass is not merely dark in light, it remains dark in essence. As the subject settles, the larger structures of the universe seem calmer again. Galaxies drift in halos they do not reveal. Clusters bend light with mass that does not shine. The broad web of matter stretches across darkness, carrying the bright worlds within a deeper framework. At every outer level, dark matter appears through gravity, through motion, through the shaping of structure over immense time. It remains one of the most consistent unseen presences in modern science. And yet the centre of the mystery stays quiet. No clear particle rests there. No final hidden substance stands fully named. There is only the steady recognition that the luminous universe is not the whole. The stars, gas, and dust are the visible surface of a larger arrangement. Beneath them lies matter that outweighs the familiar and still keeps its nature concealed. So the mind leaves the problem where astronomy now leaves it, between strong evidence and open identity. The cosmos appears heavier than it looks, more structured than light alone can build, and more inwardly strange than first believed. In that calm uncertainty, the dark universe remains vast, ordered and unfinished, waiting in silence for its deeper form to be known.